All right, General Chemistry, it's good to be back with you, and I hope you're doing well and staying healthy as we start our first week of online learning. I'm going to be posting videos to help you guys out, and I'll be answering questions via email, or you can post on Google Classroom and I'll answer those questions. Let's go back to our gas laws here. That's what we've been working on, and I want to look at one example here to describe our next topic. This is something that some of you might be familiar with by experience if you've been in a car accident. This is the airbag in the car. And this airbag has just deployed, and you see this fine white dust in the air going up. If you've experienced this, you've seen that fine powder in the car as well. But this airbag, the whole reason it works is because it fills up with a gas. And that gas prevents you from hitting a hard steering wheel. You hit the soft airbag instead, and it distributes that force all the way across your body so you don't have a force on a really small area. Now, I don't know if you've ever wondered this, but where does that gas come from for an airbag? Is the gas in the car in a CO2 cartridge, kind of like a paintball gun would have, or an airsoft gun, or is there some other mechanism for filling this up with gas? Is there one cartridge and there's lines that run to every little airbag? We're going to answer that question today when we look at gases. So the topic for today is something called gas stoichiometry. Oops. And gas stoichiometry answers the question, how much gas gets produced? Or, if we're doing a chemical reaction that uses the gas, how much gas do we need to get what we want? And this has tons of applications. Airbags in a car is one of those, but this picture in front of you right now is an industrial plant, and many industrial plants do chemical reactions that involve gases, either producing gases or consuming gases. And if you're in charge of running this industrial plant, those gases are being piped across the plant and into closed containers. And that means if I'm producing gas in a closed container or consuming gas in a closed container, I have potential for getting extremely high pressures or low pressures if I am not careful on how much I'm producing. So the person running the plant needs to know exactly how much gas gets produced for a chemical reaction or consumed by a chemical reaction. And that concept is gas stoichiometry. And we're going to look at how to do gas stoichiometry today. So before we do that, quick refresher on what stoichiometry was. We did mole-to-mole conversions for chemical reactions, and let me just write a balanced chemical reaction here. Let's say we have compound A plus B turns into C plus D. And I care about compound A and relating it to compound B. Well, these two compounds, both reactants in this case, the only way to relate these two was to be in units of moles. And we talked about that extensively, always be in moles, use the balanced equation, or ratio, so maybe I have a 2 here for 2 moles of A for every mole of B. And we did lots of problems where we started out in grams. We had to convert to moles using the molar mass off your periodic table. Once we were in moles, we could go into moles for our other compound, and to grams and atoms or molecules. So we've been on this part of the table for quite a while. We've also looked at our liters of solution. We could use a molarity, which is a moles per liter, and we could start with liters of solution, convert it into moles, and once we're in moles, go from moles of one compound to moles of another compound, and get back to liters of solution. We're going to add to that now liters of a gas. And liters of a gas, we're not just going to do it at STP. We're going to generalize this. So this would be, we could just write our volume of our gas here. If you're given a volume of a gas and you want to do a chemical reaction with a gas, we have to treat it a little bit differently to get to our moles. And the only difference here, if we're not at STP, we're going to use the ideal gas law. And from the ideal gas law, you need to know the pressure, the volume, and the temperature. And if you know these three things, you can solve for the number of moles using the ideal gas law. And then we could do a mole-to-mole ratio just like we normally do in stoichiometry. And this connection allows us to do stoichiometry with gases. So you could start with a gas that gets consumed, or you could end with a gas on this side, and we could use the ideal gas law to determine what volume of gas might be produced at a given pressure, temperature, and number of moles. And you get your number of moles by doing the stoichiometry for maybe a solid. We take a solid in grams, go to moles, convert to moles of the gas being produced, use ideal gas law with the moles produced, temperature and pressure, and tell the volume, or you can calculate pressure. So that's what we're going to do here. And let's go back to our example of this airbag. The airbag is not produced, the gas is not produced by a CO2 cartridge. It's not pressurized gas. It's actually a chemical reaction that's sitting and waiting in all of the closed spots of your car. It's waiting for the opportune time to react and produce the gas that we need, nitrogen gas, to fill the airbag. And that chemical reaction looks like this. There's little compounds or little pellets in there called sodium azide. And that's our sodium azide compound right here. It's sodium attached to 3 nitrogens. Well, this is unstable. And it's so unstable that once it starts to react, it's a very quick reaction. And in your car, there's a little crash sensor that senses if you get in a car accident by measuring the acceleration of your car. And if it senses acceleration is too high, it will send electricity through this sodium azide. And all at once, that sodium azide reacts, and it produces sodium solid and nitrogen gas. Well, this is what we care about. The gas is what fills up the airbag, and that nitrogen gas fills up our airbag to cushion our slowing down in our car so we don't hit the steering wheel. The sodium, this solid actually goes off and reacts with H2O in the air, and it produces NaOH, sodium hydroxide. And that's what this little white fine powder is in the air. It's sodium hydroxide. It's reacting in the air, and it burns your eyes and burns your nostrils if you've ever been in an accident. That's what that is. But what we care about in this problem, we want to know about our nitrogen gas and our sodium azide. And let's say that this is our problem. The nitrogen gas in an automobile airbag with a volume of 65 liters. So our airbag's filled right now. This would be after it reacted. We have 65 liters here. And it exerts a pressure of 829 millimeters of mercury. So my pressure, 829 millimeters of mercury. And we have a temperature, 25 degrees Celsius. What amount of gas in moles is in the bag? So we've got a pressure, a temperature, and a volume here. Put V. We can use the ideal gas law to solve for this. And then how many grams of sodium azide were originally in the airbag device? So we're going to go from our sodium here, or nitrogen, back to our sodium azide once we know the moles using stoichiometry. And that's all there is to gas stoichiometry. So the first thing we want to do here is calculate our number of moles of gas. And if we're given a pressure, volume, and temperature, we're going to use the ideal gas law. P times V equals nRT. If you remember from 2 weeks ago, our R is a constant. We're going to be solving for the number of moles, so I'm just going to call that N. R is a constant, 0.0821, and that constant has units of atmospheres times liters per mole times Kelvin. These are the units that everything else has to be in our problem. So the temperature for this particular problem needs to be in Kelvin. We're in degrees Celsius. To convert that, you add 273.15, and that comes out to 298.15 Kelvin. We're going to plug that into our ideal gas law. The volume was given to us, 65 liters, and the pressure needs to be in units of atmospheres, and that's from our ideal gas law constant. And to convert to atmospheres, you divide this by 760, and I'll just write that in here. You can do that on your own. It's 1.09 atmospheres. From this given information, we can calculate the number of moles of nitrogen gas that were in that bag. And the number of moles of nitrogen gas that were in the bag comes out to 2.8965. I'll just write out a couple significant figures here. This is moles of N2. This is not our answer, so we won't round this. But I want to keep going from here. So I've done my first step. I've converted from the ideal gas law. And if we go back here, we're starting with the volume of a gas. We were given pressure, volume, temperature. We converted into moles. I'm in moles of my compound. Now I can do my mole to mole ratio. That's my stoichiometry to go from moles of gas to moles of the other compound in my problem. In this case, we want to go from moles of gas to moles of sodium azide. So I have a 2 to 3 ratio here for moles of N2 to Na3, and let's convert this. 2.8965 moles of N2. And I want to get out of moles of N2 into moles N3, sodium azide. Go back, make sure I have my ratio correct. 2 to 3 ratio. 2 moles sodium azide for every 3 moles of nitrogen. And then I want to get out of moles of sodium azide. It asks me what's the mass. I want to get to grams. So we'll get out of moles of sodium azide. 1 mole of sodium azide, if you add that up on the periodic table, it's 60 What are we here? Sorry. 65.02. And if you calculate this out, you get 125.6 grams. And with sig figs, we would round to 130 grams of sodium azide. What is that? That's the mass required to be stored in your steering wheel, ready to react to fill an airbag with 65 liters of nitrogen gas at a pressure of 829 millimeters of mercury at 25 degrees Celsius. And what they actually do is they do several chemical reactions. They don't just go off the stoichiometry number. They put more than that in there. And they'll do tests with it to make sure that it gets the pressure that it's supposed to get. There's little holes in the airbag so it deflates, so some of the pressure, some of the gas actually escapes when it reacts. So that's how you do a stoichiometry problem with the ideal gas law. The other version of, here's what our sodium azide looks like. These little pellets in here, they're stored in there. The other version of ideal gas law is to go from a mass of a compound to the gas. So in this one, if 14.5 grams of magnesium is placed in excess HCl, the acid magnesium will react to produce hydrogen gas. Let's write our chemical reaction first. Magnesium, solid, reacts with HCl. This would be an aqueous, so we'd put it into a solution. And this produces magnesium chloride. It's a single displacement reaction, plus H2 gas. And the H2 gas is what we care about in this problem. If we balance that, we need 2 of these, and everything else stays as a 1. If this gas is trapped in a balloon, there's a volume and a temperature. We only get 2 pieces of information. For ideal gas law, you need 3 of the 4 to solve for the other. So if we're only given 2, we should be thinking we must need to start with this number here. And we're going to go from grams of magnesium to moles, moles of magnesium to moles produced of H2, and then from moles to what they're asking. We want to know the volume. So we're going to solve for the volume using ideal gas law. So let's do that. We'll take our 14.5 grams of magnesium. Using your periodic table, you'll find that there's 24.31 grams of magnesium for every 1 mole. For every 1 mole of magnesium in our problem, we produce 1 mole of H2. And if you calculate this out, you get 0.5964 moles H2 produced. Now we want to know the volume of this. We have the moles. The problem gave us the pressure and the temperature. We're going to solve for volume using ideal gas law. So our pressure is 698 millimeters of mercury. Divide by 760, and you get this, 0.918 atmospheres. We're going to solve for the volume. That equals our number of moles, 0.5964, times our ideal gas constant, 0.821 atmospheres times liters per mole times Kelvin, times our temperature. And our temperature was 21 degrees Celsius. So that comes out to 294.15 Kelvin. And if you solve for your volume here, you get a volume produced of 15.89 liters of H2 gas. With sig figs, we would round that to 2 sig figs, so we would say 16 liters of H2 gas will be produced if 14.5 grams of magnesium react with excess HCl. And those are 2 ways to do gas stoichiometry, starting with a gas or starting with a compound like a solid and going to the gas. So if you have any questions for how to do those problems, feel free to ask. I'll show 2 special cases on a separate video, but these are the general cases to solve any type of gas problem involving a chemical reaction. Thanks.